Hello everyone. Today we will be embarking on a journey. I will be taking you through every single thing to know about computing theory for A-levels. So I came up with this document in National Library one day and it carried me through A-levels. 16 pages of the densest, most condensed, but most comprehensive notes for H2 computing. And I'll be going through all of them with you because I would do that for you guys. So yeah, this has information from VJ notes, from other school notes, from test papers, past year papers, comments my friends have given, online, Googling, ChatGPTing, a lot of different sources. And it's pretty comprehensive. I don't think there's any anyhow knowledge in here. I'm pretty sure everything is proper and standard. So let's kind of go through this. First, let's start with the databases. Databases are, I guess, not that hard to do for theory, so don't worry so much about it. Just worry a bit about the normalization and it should be fine. So yeah, tables. Tables contain fields, records, and attributes. Fields are columns inside of a table like in SQL, and records are rows. Attributes are slightly different because attributes are a bit more dynamic in nature. Certain things, for example in NoSQL, certain entries have attributes that others do not have. So it's a more comprehensive, definition. It just is any sort of a row title, anything that belongs to the entry, rather than fields in which you have a strict number of things that every single thing has to fulfill. So for example, if you have one entry that is Josh, right? And it has Josh's phone number and his favorite book to read, versus if we had, for example, Dylan, and for Dylan it was just his phone number and nothing else, then while Josh's favorite book to read would be an attribute, you can't necessarily call that a field because you can't represent it inside of a SQL database. Then we have redundancy. Redundancy is the idea that the same data should not be stored more than once, because it can lead to data inconsistency. Then we have the relational database format, which is basically table, and then in the brackets, attribute 1, attribute 2, etc. You must underline the primary key and dot underline the foreign key. This is a very important distinction you have to do for A's. Just keep this in mind, and don't forget primary keys and foreign keys. I'll explain now. So for relational databases, right, a key is a column that uniquely identifies a row. So this basically is a way for you to pick out an entry and identify it based on a bit of information that you're given. So a candidate key is any column that identifies a specific row. So it could be, for example, an ID. And then a primary key is a set of columns that identifies a specific row. For example, if there is 40 register numbers per class and 32 classes per year, right? Then 23S56 register number 17, for example, is enough to identify, I don't know who it is, it might be me, but it's enough to identify that person. So yeah, it's like that. Then secondary key is any candidate key, right, that isn't a primary key, which means any identifying key that is not specifically used as the primary key. And then we have foreign keys, which is just an attribute in a table that refers to a primary key in another table. So that is again a whole other thing. Like let's say if we have another table with exco roles, and there is one that names someone as the president of a certain club, then that could be represented inside of their academics table, for example, except it would be a foreign key because it's a primary key of a CCA table inside of a completely unrelated different table. Then we have normalization, and normalization, I would say, is pretty standard. 1NF is atomicity. 2NF means that it is in 1NF and has no partial dependencies. And a partial dependency is, again, you can think of it this way. It's like the conjunct primary key I told you about. Like if I was from 23S56 register 17, you're using two different things. So the primary key is dependent on two different things, two different fields. Same thing over here. That is a partial dependency. So not having partial dependencies means instead of saying 23S5617, you would just have my T0 whatever. Yeah, like my username or my ID, my school ID, something like that. Then yeah, 3NF is having 2NF, which means 1NF and no partial dependencies, plus no transitive dependencies. A transitive dependency is kind of like if column X depends on column Y, which depends on column Z, because that's kind of useless. So yeah, keep that in mind. Then we have entity relationship diagrams. One-to-one just means that it's one-to-one. I mean, you've learned this in functions in math. It's not that bad, I would say. Then CRUD is just your create, read, update, and delete operations. And your database operations, use these for languages. Data definition language, which defines. Data manipulation language, which changes. Data control language, another kind of change. And transaction control language. I don't think I've seen anyone ever test this before, but just keep in mind this is something that's testable. Then this is the anatomy of a database. Inside of a database, you have multiple different tables. That's kind of what it looks like. Now, moving on to theory 2, non-relational databases. So, non-relational databases like your, for example, Mongo, work slightly differently. So, firstly, you have ValueDB, then DocumentDB, Wide Column DB, and GraphDB. You again need to know these, but I've never seen them tested before, so just know these. Then you have your ACID properties, which are atomicity, consistency, isolation, and durability. And your relational database contains documents, which are your rows, and fields, which are your columns. It's very JSON-like, I would say. So yeah. Non-relational databases have some advantage and relational databases have some advantage. So in NRDBs, they have no predefined schema, which means it's very dynamic. You can kind of add whatever you want. There's a hierarchical storage, there is horizontal scaling, which is different from vertical scaling, horizontal scaling, and storage in many servers. So horizontal scaling refers to this. Assume I have a storage brick, which has a bunch of memory and stuff, which stores all of the stuff, right? I don't need to upgrade that brick. I just need to put another brick beside it, and both can hold everything. You don't need to upgrade directly that one server you have. You can just add another server. That's what horizontal scaling is, compared to vertical scaling, which just means you have to keep making the computer bigger and bigger and bigger, instead of just adding computers. So for relational, the advantages are structured data, so it's very clean. Complex querying, which means you're allowed to kind of make a bit more complicated queries with all of your selects and all of your weird stuff that SQL allows you to do. And then you have data integrity, which is made sure, basically, which is, yeah, good. Then, yeah, a database anatomy is very similar, database collection. Now, moving on to web applications. There are a few types of web apps. Natives, which are installed onto your device, like, for example, Geometry Dash. Web apps, which are internet-enabled and need browsers. Hybrid apps, which are native wrappers but use the internet. So for example, most I would say online games, because they use the internet but they are fundamentally native. And progressive apps, which can be made into a shortcut and turned offline. Like I believe this can be done with the LTA bus app, I believe. Sorry, the LTA bus website. Don't fact check me on that, I could be wrong, but yeah. Then native apps are developed for specific operating systems, Linux, Mac, etc. Need to be installed, have access to GPS and RAM, and no need internet to function. They're faster, safer, and well, they have maintenance and updates costs, unfortunately. So for web apps, however, you just need a web browser, that's all. You don't need to install it, and it has no access to GPS or camera. Sorry, not RAM, camera. And you do need internet for it to function, but it can be slow because of this. It's less safe because you have the threats of the open internet, and it's updated automatically. So you don't need to keep pushing things to users for them to update so that they can use the software. Then we have Jacob Nielsen's usability principles. Oh my god, I hated this so much. Charm few V. Consistency, help and documentation, aesthetics, recognize, don't recall, match to real, flexibility, user freedom, visibility of system status, error recovery, and error prevention. So I'll just explain a few of these that were difficult. Help and documentation is, again, simple. Consistency makes sense. Aesthetics, just look nice. Recognize, don't recall. It means if you see a camera icon, you should not be thinking, I wonder what icon that is. You should just know, oh, camera is camera. It's camera. It just makes sense. Oh, I see a mic. It's audio related. Oh, I see, I don't know. I see the Wi-Fi symbol. It's Wi-Fi related. Yeah. Then match to the real world, kind of just contextualizing it to the real world, making words make sense, making pictures make sense. And yeah, I mean, the rest of it kind of makes sense. Flexibility, user freedom. Visibility of system status is a bit interesting. This is when you're navigating inside of the app and you can kind of tell at what point you are inside of the app itself. So yeah, don't get that confused with like error recovery. But error recovery is when things go wrong, what can be done, and error prevention is how easy is it for you to, how difficult is it for you to actually encounter an error in the first place. So then you have character sets. ASCII is 128 characters, 031 are non-printable characters and 7 bits long. Then Unicode is 155000 distinct characters, which includes your weird Russian letters, your Chinese characters, and those symbols that people use in usernames that you just wonder, oh, how did this show up? So yeah, there's that. And it's longer, of course, but it's more comprehensive. So if you want extended language support, you should be using Unicode. Then you have, again, functions and recursion, theory 4. Amazing, we're doing great, guys. We have subroutines, which are functions. Subroutines have functions which have return values and procedures which have no return values. That's the difference. That is the difference. Keep this in mind. So, again, a parameter, right, is an expectation. Okay? If you put a definition like def do something, right, the parameter is what you will be using. It's not the value that's actually passed in. It's what you expect. The value you actually pass in is called an argument. It's a completely different concept. Now, these two are called initializers, of course. And yeah, variables, you have global and local variables. Global variables are a pain to deal with in programming. I believe in my prelim I lost a couple of marks because of that, so just keep that in mind. It's a bit difficult. I might put a tutorial on that later, I don't know. But yeah, for local variables, they're defined within a structure or function, and for global, they're defined outside of a structure or function, such that no matter what rights you have, you can access them. So then, yeah, recursion. Recursion has 3 principles, and you must memorize this because people love testing this. It's defined within itself, it calls itself, and it terminates when it hits base case. You might be wondering, doesn't this kind of overlap with each other a bit? Yes, it does, just deal with it. I want marks, you want marks, let's get this over and done with. So then, you can use trace tables as a way to explain recursion. It's in call numbers, calls, and basically anything. Your trace tables are a bit flexible. You can kind of just write whatever you want. The more information, the better, as long as it's not irrelevant. And you have to remember, executions for recursive functions use stack frames to push and execute commands until the base case is reached. Then they are popped from the stack. So it uses the stack data structure. Trace trees are slightly similar. Call something, hits the end, and then it keeps pushing backwards until you reach. Yeah, it's pretty simple, it makes sense. That's about how much it is. Then yeah, next you have theory for algorithms. This is a lot of people's worst nightmare. Okay, for context, I will not be explaining how each algorithm works. That will be explained in another video. Maybe I'll do essential algorithms, which will take a while, but I will probably explain it then. But for now, you just need to know the theory parts of it. So for bubble sort, again, worst case is n square. It can be optimized using this thing called swapped, right? Which allows you to ignore certain comparisons that you have already made. You want to go Google this? You can. You need to learn this, but it's going to be on essential algorithms and not in this file. Then you have, it iterates I and iterates j until I, so it kind of makes sense. Then you have insertion sort, which has an n square worst case. It holds a swappable element and shifts it into the right position. Best case scenario, it makes no comparisons. You see, bubble sort in best case scenario is still gonna make comparisons, but insertion sort will not. Then quick sort is O(n) squared, worst case. This is faster, right? But again, it's still worst case O(n) squared. So it can be in place or out of place, which is recursive. If it's in place, may God help you. It reconstructs arrays based off of the pointer, and if it's nearly sorted, you have fewer comparisons. So quicksort is pretty common, a lot of people test it, yeah. Merge sort's a bit different. Merge sort, no matter what, will give you n log n, because it always splits depending on how large your array is, or your list is. It's a divide and conquer recursive one. It splits arrays into elements by splitting them into smaller and smaller arrays until they split into elements, and merges them in the right order to reconstruct, which is one of my favorite algorithms of all time actually. because it's so beautiful. It always takes some time it always takes the same amount of time no matter what the level of sortedness it is. So it's very reliable and consistent. Then we have search algorithms. For linear search, again, it's O of n worst case because you need to go through every single thing once. And for binary search, it's log n worst case. So for binary search, you need it to be sorted. That's the problem. But it cuts the search window in half every search. You can think of it like a dictionary, kind of. Like an actual physical dictionary. If I searched for, let's say, the word water bottle, right? I wouldn't go looking from A, B, C, D. I'm not going to do that. I will look at W, right? And then from there, I would kind of cut it in half again, and use a smart method of searching rather than going through every single one. So yeah, it goes to the exact middle, checks whether it's on the left or the right, goes to that segment, and then repeats the process by going exactly to the middle, checks the left or right, and then does that again and again and again until you get to the element that you're looking for. Or if you don't, then it'll give you like a element not found, that kind of thing. So yeah, it repeats until the left pointer crosses the right pointer. You can think of this as two pointers that keep shifting. So if you want to like move to the left, like I told you, you just shift your right pointer, and if you want to move to the right, you just shift your left pointer to the middle. So yeah, it's that. It's significantly faster in larger data sets, and yeah, it's due to having search window is log to it. Then we have control flow. Decision tables, again, you've done this so many times. Come on, you got this. Just remember, like, you have to put an X, not a tick. Please don't put a tick. That will be the worst way you can lose marks, genuinely. Then you have flowcharts, which is just start and then input. Again, you need to use a rhombus for inputs and outputs. For comparisons, you need to use a diamond. For events, you need to use a square. And then your start and end, you need to put a circle. Yeah. Okay, I'm gonna take a commercial break. I'll be back. Welcome back, everyone. I'm back. My throat is starting to hurt because I've just done filming all day, but it's fine. So for theory 7, is it? I don't know. It's either 6 or 7. Oh my god. So yeah, I walked right into that one, didn't I? Okay, whatever. So this is for storage and memory, right? Firstly, types of files. You have two types, serial files and sequential files. Serial files are records that have no defined order, and sequential files have a defined order. It's that simple. It's just unsorted and sorted. Now, for file paths, you have an absolute path and a relative path. So, for example, this link you can see on my screen right now is an absolute path because it starts from something and keeps ////. But if I removed it all the way to here, that's a relative path. Relative path, or if I go until here, it's a relative path with respect to drive. So a relative path is with respect to another file. But an absolute path means if I just go to the base root of the computer and I just throw the path in there, it can tell you exactly where the file is. Now we have shallow copy and deep copy. A shallow copy only copies the memory value of something. So if I have, okay, let's say my friend does his computing homework and I don't do it. If I shallow copy, right, if he deletes his file, mine gets deleted too. If he changes it, mine gets changed too. But if I deep copy it, it means I literally copy everything from his file, which means even if he changes it, mine doesn't get changed. It's a different file, not a mirror of his file. That's the difference. Now, there's advantages of static and dynamic memory. One is stack-based and one's heap-based. For static, you need to know it has faster access as memory is allocated at compilation. Then it prevents memory fragmentation due to the fixed size, and it improves cache performance because data is in similar locations. Now for dynamic memory, it's heap-based. It's flexible memory reallocation and reusability because you can kind of just pick and choose wherever you want. Scalable as data need not be predefined, and it's safer for larger data structures as it avoids overflows entirely. I've talked about overflows in other videos, which is when you write data above the amount that the computer is expecting. So yeah, keep that in mind. Theory 8, I think 5 to 3, 8, yeah. So theory 8, data validation and verification. We're reaching the end, don't worry. So first we have input errors. Input errors are errors that can be made because of input. Wow, that's stupid. It's errors that can be made because you are trying to add value, to add some sort of data in a sense. So transcription errors are basically when you accidentally change something. So like an L was changed to an O here by accident. And then a transposition error means fundamentally it's the right thing, it's just in the wrong place. So yeah, that's the difference. Keep both in mind. They can test this. Actually, they have tested this many times before. Oh god, I hate this chapter so much. Validation, verification. Okay, great. What is data validation? It ensures that data satisfies a set of rules. Data must be sensible, complete, and within bounds. Keep that in mind. There is range check, which checks, for example, is your thing within 0 to 10. Format check, which checks is it a string, is it an int, is it something else. A length check, is it above 15 characters or below 15 characters? A presence check, does it exist? And a check digit, which I'll get to now. A check digit is a way for you to verify that data has been correctly stored and not tampered with. Let's assume I want to store 314159, right? To prove that this is a correct sequence, right, and check it, how I can do this is by taking the position of every single one of them from the back minusing 1. So 9 would be 2, then 3, then 4, then 5, then 6, then 7, multiplying each of them, so 3 times 7, 1 times 6, 4 times 5, 1 times 4, 5 times 3, and 9 times 2, and adding them all, right? Mod by 11, 11 minus that, and mod 11 again to get a number. It's a bit confusing. It's just mod get minus and mod. Then you have a number at the end. And then with that number, you just chuck it at the back. So now you have something that you can use to verify. How do you verify it? Well, you do the same thing as you did just now, except you treat the checker number as an index of 1. So instead of doing 9, 2, 5, 3, 1, 4, you do 4 times 1, 9 times 2, 5 times 3, 1 times 4, etc. all the way to the front. And then if you add them all up, you should be perfectly able to mod it by 11. That's how a check digit works. It's also how you verify, for example, credit card numbers. Imagine you go to like Roblox or like some weird website that you want to spend money on, right? And you don't want to spend your own money, right? You want to buy Robux off of some random guy's account. So you just type in a bunch of random numbers. How do they know whether that's an actual credit card? Well, they do this check. They basically have their own sort of check, similar to a check digit, that verifies, is this sequence of numbers sensible? Does it make sense for this sequence of numbers to be a credit card number? And if it's yes, then, well, I guess that guy's losing money. But if it's not, then I guess free Robux? Sure. So verification. Verification is ensuring that the entered data was intended and entered in the same way it was intended to be entered. This is just making sure you enter it right. So there are two ways of doing this. Proofreading, which is open your eye big, and also double entry. Double entry is commonly used in password checkers, where they ask you, enter your password, re-enter your password, and if they mismatch, they warn you. Now, test data. There are 3 types of test data: normal, boundary, and abnormal. So there is a common misconception, okay? Which is boundary data abnormal or normal? Here I clarify for you. Boundary data is normal. Boundary data is on the boundary, which means it is acceptable but on the boundary. Abnormal is not even in the boundary. Abnormal is different. It's just wrong data. Does that make sense? Great. So yeah, boundary data is the actual ends. It is not above the ends. It is the ends. So yeah, then syntax error is just wrong grammar, stuff's not gonna run. Logical error means that there is incorrect output due to a logical error and will still run, and runtime error means there's valid syntax, right? There's valid syntax and logic, but the environment has an error. Maybe it's recursion, for example, and it will crash. So will not run, and will crash. That's the difference you need to keep in mind. Moving on to IX. Is this 8? Might be 8, I think. Or is it something else? I don't know. No, it's 9, right? No, I don't know. Oh, it's 9. Yeah, it's 9. So then we have object-oriented programming. Okay, here's where stuff gets a bit more confusing, because from this point onwards, the notes are going to get really dense. First, you have classes. Classes are blueprints for an object. Blueprints, okay? They're not actual objects. If I have a class, you can think of it as a sketch on a piece of paper. It tells you how to build an object. It helps you build the object, but it is not the object. The object is an instantiation of the class. So if I have a blueprint to help me build a Lego set, I can't call the blueprint a Lego set. Then you have the mechanisms behind it. Oh god, get ready because this is confusing. Encapsulation. Encapsulation is the bundling of data and methods within a class. It restricts access to private attributes with public methods. This means that you cannot just anyhow go dig into whatever variables you have and set them and get them however you like. You need to use public methods to dig and mess with private attributes. This separates interface from implementation. You have to say this, by the way. Then inheritance. Inheritance is it just enables child classes to access public methods from parents. So let's say we have like sports person, right? And that person, sports person, has like a bunch of different methods or attributes. Inheritance allows football player to inherit everything a sports person has, plus their own specific football specific things. So it promotes code reusability and reduces code duplication. Keep in mind, you have to say all of these things. For all of the pointers I write down, they're all exactly the keywords you have to say. Then you have polymorphism. Polymorphism is the redefinition of a method in a child class with different behavior from its parent class. This promotes code generalization and reduces complexity of code. You want more info, go to Essential OOP. I think the video should be out. I don't know, maybe it's not, just wait a while. It'll come out. But yeah, that is something you have to keep in mind. Oh god, class diagrams. Yeah, here's what a class diagram should look like. Again, the arrow should point from the top of one to anywhere on the other. I just did it like this because it's easy. Then yeah, dog inherits from animal. So animal has name and legs. Dog has name, legs, and owner. So even if dog does not have name or legs declared on its own, since it inherits, you need to state it. Then you have get name, get set name, get legs, set legs, and buck. While the original one is say hello, because maybe it doesn't inherit that one. Then yeah, data management and ethics, theory 10. Oh god, I think I need a commercial break. Hold on. Hello everyone, I'm back, and now I'm here to explain theory 10, data management and ethics. From here on out, it's gonna get really dense, so hope you're prepared. Strap in and let's go! So firstly, we have data. What is data? Well, weirdly enough, we do have to give a definition for data. Data is information that is encoded and structured for processing. Then what is information? Information is data that has been interpreted. So, if any of you like philosophy or like law or debate or even have a remote interest in English, you'd understand that you can't have a circular definition like this. It's kind of garbage, but hey, I want marks, you want marks, let's just do it. So, data integrity. What does data integrity ensure? Completeness, consistency, and validity. You need to memorize these. The data privacy, it ensures that data that is disclosed to authorized people only, which is people who either are licensed to use it or the people who request for it. The life cycle of data is creation, storage, usage, archival, and deletion. You might be wondering, what is the difference between archival and deletion? Archiving is to just kind of put something in the attic or the top shelf and not worry about it, but not discard it. Because when you delete something, it's permanently gone. Archival is just to put it aside so that if needed, you can circle back to it later, but you likely won't. So yeah, storage threats, human behavior, people being idiots. Overwriting, if you accidentally overwrite over something that was important. Unauthorized intrusion, someone breaking in. And natural disaster. Unfortunately, this is quite common in certain countries. Then we have the code of conduct, which is competence, responsibility, integrity, and professionalism, and is funnily called CRIP. Then we have NRIC. NRIC, you have to know two things about it. One, it's illegal to collect an NRIC unless it's used to verify someone's ID. And two, partial NRICs are used otherwise, but I believe the government will be slowly rolling back to full NRICs soon. I believe. Again, double check this before you use this in your exam. Legislation. The different legislations you have to know about are PDPA, Cybersecurity Act, Computer Misuse Act, and Copyright Act. If you know a really, really good lawyer like I do, then you can go and ask them about these things. But if you don't, Google's always there. You should be fine. You just need to know that these exist and how to call one of these out over the other. Then we have the protection of data. There are a few ways you can protect data. Firstly, back it up. You have to create copies of data as precautions. Secondly, archive the data. Store historical data for auditing purposes. If someone comes knocking on your door saying, on June 15th, then you gotta be prepared, right? Then access restriction, which is all of these other ways you can restrict data. And then version control, you can use git to modify a stage commit. Then validation and verification, which is again, as we mentioned in the other chapter. Encryption, which alters the data to make it unreadable unless reversed using a key, usually paired with access restriction. Or, as we do in the army, erasure. If you're about to be captured by the enemy, nuke it all. Just nuke it all. Erase everything. So yeah, PDPA obligations. Here are the obligations you need to know for PDPA. I believe in class we were recommended to memorize 5 or 6. I recommend you to memorize all of these. Like, honest to God, I recommend you to memorize all of these because they're not that hard to memorize. If you can finish your Jacob guys' different principles, then you can probably memorize this as well. Just don't worry too much. Just practice it and you'll be fine. So there's purpose limitation, which is about the disclosure of collected data. Accuracy, which says that all collected data must be accurate. Protection, all collected data must be securely protected. Accountability, make information on protection policies available if asked. Remember, accountability is not about stuff going wrong. It's just about transparency. Consent, which is ask for consent before using or disclosing data. Access and correction, if someone requests your data, right, give it back to them in 1 year. Notification, which inform users before collecting, using, or disclosing data. Again, not the same as consent. Consent is asking, notification is telling. Then you have transfer limitation, which is if you're bringing it overseas, make sure it's legal. And retention limitation, make sure that users are not strictly tied to the data, such that if they want it to be deleted, it can be deleted just like that. Oh god, get ready for networks. The rest of this is going to be very hacky and cybersecurity, so good luck. I don't know how much of this to remember, but let's go, full speed ahead. Okay, computer networks. Firstly, what is a network? It's a system of more than 2 computers connected by a transmission medium. Could be a wire, could be wireless, it depends. A LAN, which is a local area network. It's a network of devices in a small geographical location. Then we have a metropolitan area network, which is network of devices in a larger geographical area. Then WAN, wide area network. A network of multiple MANs and LANs across multiple countries or continents. An intranet is a private network built in an organization for secure information sharing amongst authorized users. A very famous example of this is one that none of us can talk about without it being censored. The internet is the global public network accessible to anyone with an internet connection, which is the one we all know and love and hate. Then we have network hardware. NIC. NIC is a chip. It's a chip inside of your computer that has a MAC address. It allows wireless transfer between the device and the network. Then we have the UTP cable, which is a standard cable for electrical transmission. It is just a cable. Then you have a hub. A hub is similar to a switch. A hub connects devices within a network, manages data flow, and shouts the received packets to everyone. A switch does the same thing, except it doesn't shout received packets. It just logs the MAC addresses. So a hub is like a megaphone kinda, and a switch is just a messenger, but they do the exact same thing, which is connecting devices within a network, usually between a router and a device. Then we have routers. They connect to LANs, right? These networks, connect to networks, assign IP addresses, and direct packets. Those are the main functions that they do. Beyond this, we have WAP. These are wireless access points. They're devices that just create WLANs. A WLAN is not the same as a WAN. Then we have a modem. A modem facilitates signal conversion and reversion. Modem stands for mod-dem, which is modem, modulation, demodulation. It's a modulator, demodulator. That's what it does. You can think of it as electricity to data, data to electricity, something like that. Now, network addressing. There are a few kinds of networks you need to know, or I guess network addresses you need to know. Then we have MAC addresses, which are static, they do not change. I mean, MAC spoofing is a thing, but you don't need to worry about it. It's 48 bytes, and it's given by your NIC chip. This has 6 times of double alphanumeric. So it's like 1A, 4C, something, 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 3C, that kind, 6 times. Then you have IPv4, which is dynamic, 32 bytes, given by the router to the device. So it's again 255, 255, 255, 255. All of those like memes about DDoSing people, this is using IPv4. IPv6 is newer, 128 bytes, and it was created because there was a shortage of IPv4 addresses. I believe it's because on the open internet, there's just not enough IPv4 addresses left. So it's again given by router to device, and it's 8 times of a 4 alphanumeric. So it's 14A6, something, 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 8 times. Now you have the TCP IP model. This one is infamous. A lot of people can't memorize this. Please memorize this and make yourself very familiar with this. Actually, I dare say, if you know how to do TCP IP model properly, like you properly understand it, the entirety of networks and like net security, that entire chunk, like 25% of H2 computing is yours. Like if you understand the TCP IP properly. So firstly, you have the physical layer, which is about physical transmission of data over wires. Then the data link layer, which repackages data into frames, small frames for devices in the network segment. So things in this layer are the NIC chip and the switch. Then you have internet. They route packets across different networks. That's the layer this is in. So it's like your routers. You have to understand, the internet doesn't exist. It's just a bunch of routers talking to each other. It's like a couple million routers just talking to each other. That's all. That's all the internet is. It's not some fancy big station exists. It's just routers talking to each other. Then transport layer. It manages data transfer between applications using TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. Then you have the application layer. This provides services directly to your apps, such as your apps, your OS, your browser, etc. So this is generally what your thing is going to look like. Computer will go through a WAP to a switch, printer will go to the router, and the switch will go to the router. This is generally what the hierarchy is in one tiny wing of a large map. I forgot what it's called, but your network map that you have to draw out. Yeah. And also remember, when you ask you to draw out on these maps, you don't need to actually draw the computer or the printer. I did that once. My teacher thought it was kind of funny, but like low-key, I didn't lose marks, I think. Whatever. It's fine. Just write computer A, WAP, switch, that kind. My favorite part, memorizing the different protocol names. HTTP, Hypertext Transfer Protocol. It requests a web page, returns 200 if it's okay, and a 404 if it's not okay. FTP, File Transfer Protocol. It is used to upload and download files, pretty simple, pretty standard. IMAP, Internet Message Access Protocol. It synchronizes emails with servers. SMTP, Simple Mail Transfer Protocol. It's supposed to be used to send mail over to a mail server. For the mail related ones, you will use them very rarely, but you have to learn them. I believe they came out one time. I don't remember exactly how, but I remember they came out in one of our exams. Might actually be A's, I'm not too sure. Then you have DHCP. DHCP is very important. It's how routers assign IP addresses to devices under them. Keep that in mind. Then we have TCP, Transmission Control Protocol, right? Which is about reliable exchange between apps. Data are split into packets, arranged at the end, and the missing ones are resent. Resent, okay, not ignored, resent. Then you have User Datagram Protocol. It's about fast exchange between apps. No one cares about accuracy, just get it done, So data are split into packets, arranged at the end, and the missing ones are just straight up ignored. Then you have IP, Internet Protocol. It packages data with host IP and destination IP and sends it off into the wild internet for it to be sent along its way. Then you have the two types of requests, GET requests and POST requests. GET only allows you to retrieve data. And post allows you to create, read, update, and delete the server data. So that's the difference. Keep this in mind for your Flask. Please keep this in mind for your Flask. Now for DNS. DNS is Domain Name Service. It's basically a machine that turns your IP address into a .com. So how does it work? And vice versa. But how does it work? So let's assume you want to go to a website, right? I don't know, youtube.com. First, you enter that in. The DNS cache is checked in your computer. If the DNS cache... Okay, so all of these tables, right? They refer the thing you typed, which is youtube.com, to the youtube.com IP address that exists somewhere. So first, it checks the DNS cache. If it doesn't find youtube.com there, the request is sent to the recursive DNS server at your ISP. Then, the recursive DNS server is checked. If it's not found there, the request is sent to the root DNS servers. Then the root DNS servers are checked. It's the TLD server which is checked, which is like, there's one for .com, one for .net, etc. It refers it to the correct TLD server and is checked, which then refers it to the authoritative server, and the request is processed. It will end there, okay? It will end at the authoritative server, because that's where everything is. And every time the response travels back by one step, it caches it. So if you are revisiting youtube.com for the first time, it'll cache it at the root server, at the DNS server, at the recursive DNS server, at the ISP, everything. And yeah, it'll be like rendered on your computer. So anytime you go to a website that you've not been to in a while, and your computer takes like an extra 1 second to load it, think about how much your data is being like shot across the earth and like checked with everything just so that they can get your stuff done. It's amazing. Oops. Then we have process network interface. What's a socket? A socket is a software interface where data is exchanged between the process and the server. Then you have it's just an interface between the application and transport layers. The protocols such as TCP and IP reduce lag and data chop-ups. And it's bi-directional. Sockets are bi-directional. It needs one IP and a port address. Just remember your socket code when you do this. The video should be up by now. Okay, there are two types of architectures when it comes to sockets. One, or I guess not sockets, process network interface. First, client-server architecture. This is like your google.com or youtube.com or whatever website you want to use, or your Destiny 2 server somewhere. It is one big giant brick that everyone's computer talks to. It's centralized management, very reliable, secure, and scalable, which is why it's good. And the another approach is P2P architecture, which is what you are programming with your socket. Because this effectively is computer to computer. You can think of this as Bitcoin mining, for example. It's cost efficient, right? It's available. If one thing dies, like for example, if you're playing Destiny 2 and the server goes down, everyone's cooked. But in here, if one connection goes down, then it's not that bad. Low distribution is more even, and it's decentralized, so it doesn't stand on one authority to check everything. I'd say that's a good thing. Then we have the next one, transmission and switching. This is, I believe, 13. Yeah. Okay, packet switching. What is packet switching? In packet switching, resources are not reserved. Okay? If it's congested, packets are buffered. The internet itself is a packet switching based network. So, there are a few things that you have to note. One, store and forward. Each switch waits for all packets before forwarding the next packet. So, if you have switch A and switch B, everything's traveling from switch A to switch B, right? Then everything's gonna wait at switch B before the whole lot moves to switch C. Then you have packet loss. Packets are dropped if buffers are full. So if the buffer is full, no more space left, the packets just drop. There's no choice. Congestion. It reroutes buffer packets if it's received faster than processable. So assume something somehow makes it die really fast. It'll tell you, you know what, take an alternative route, take a walk for a bit, come back. That's what congestion is. Lost packages. If a destination is unreachable, packets are sent to a default device, looping until the time to live expires. Which means if it's unreachable, it's not just gonna remain on the internet forever, circling around, collecting trash like space junk. It's going to just die after a while. Then we have forwarding tables. IP addresses in packet headers for forwarding. Then we have circuit switching. Different from packet switching, by the way, circuit switching. Resources are reserved for the full duration, not just when it is needed. Multiple switches have connections in and out, and the transmission rate is shared amongst active connections. Advantages of CS: circuit switching. Dedicated connection, so it's constant predictable. Speed, because it's really fast. No packet queue. No one's gonna wait for the whole lot. Reliability, it avoids packet loss. And long distance, no overhead for sending individual packets. For PS, packet switching, efficient use of bandwidth. Only the needed bandwidth is actually used, so it's efficient. Scalability, it grows cheap and easily. Cost efficiency, fewer resources. And fault tolerance, any failure node can be resolved through just rerouting. Welcome to Security. Theory 14. These are, I guess, it's gonna look like a lot, but it's not that bad. Okay, before we can even talk about security, we need to talk about CIA. If you're gonna study for like Security Plus or some other cert, you gotta know your CIA. Confidentiality, integrity, and availability. These are the non-compromisables of cybersecurity. Make sure stuff is secure, make sure stuff is coherent, and make sure it's available when you need it. So yeah. Firstly, ransomware. Ransomware, again, I don't think I need to explain a lot of these. Y'all are kind of familiar with these. It's when like robbers are like, yo, you gotta give me money, if not, that kind of thing. Scareware is like, oh, if you don't do this, we will do this. Yeah, spyware, adware, you get what I mean. Then we have fileless malware, which is more interesting because it hides in memory. I'm sure my reverse engineering friends would probably hate this as well. Cookies. Then we have farming, phishing. Farming intercepts requests and redirects them. So for example, if you go to youtube.com, it'll snipe you and be like, oh, no, I'll bring you somewhere else instead. Then phishing is, like those emails where it's like, yo, click here for free $1, and then you click on it and then you just get scammed, that kind. Then spamming, we're all familiar. We grew up in primary schools. We all know what spamming is. Then Trojan horses. Trojan horses are very misunderstood, I would say. They're not files that sneak into your computer and then just overthrow everything. They pretend to be harmless files. That's the only important thing you need to know about Trojan horses. They pretend to mimic Internet Explorer or Chromium or something normal. Viruses, they attach to harmless programs, modify them, and spread. Okay, viruses don't just exist, they attach to a program. So for example, if you downloaded a cracked version of, free Assassin's Creed game, pirated from somewhere, right? Then there might be a virus there, then that is attached to the game file itself. So yeah, it depends on that. Then a worm is slightly similar. It attaches to a network, consumes bandwidth, and spreads. Then we have one of my favorites. If you like low orbit ion cannon, then you will like DOS or DDoS. Denial of service, an attempt to overwhelm a website, a network, or a server with requests to render it inaccessible or slow. So every server, right, has only a certain amount of requests they can handle at a certain amount of time. So if you just keep throwing requests at them, it can overwhelm the server or even just kill the server. A DDoS, a distributed denial of service attack, is similar, except it's not one guy in his basement doing it. It's a bunch of slave bots in a botnet that are doing it. Firewalls. Firewalls are filters that monitor access. The types: hardware firewall, software firewall, host-based, cloud-based, and network-based. What do? They control traffic and maintain security. What are the applications? Stateful packet filters, app gateways which check app data, and the limitations: you can't protect them from internal threats. So if someone inside of your system, beyond the firewall, inside, codes a virus and releases it, you can't really do anything. There's a single point of failure, which means if the firewall goes down, everything goes down. And then you can't protect against threats that users allowed. If some guy decided to click yes, I want to download this pirated thing, then there's nothing you can do about it because he said yes. He overrode the block. Then we have this. We use this a lot in the army as well, IDS. So IDS is a device that generates alerts when it detects potentially malicious traffic. There are two types: signature-based and anomaly-based. Signature-based uses a library of known attacks that it kind of mixes and matches with, and anomaly-based just looks at something is sus here. Yeah, so they have completely different things. Then the use cases are alerts in Nmap, port scan, TCP stack scans, and other attacks. Then you have the demilitarized zone. The demilitarized zone is a high security zone, and that contains the high security zone inside of a demonetized zone contains web server, DNS server, and FTP server. Then a packet filter protects both of these zones, and the app gateway protects the HSZ. The IDS monitors both, does deep packet inspection and signature comparison. Placing the IDS downstream reduces the traffic load per sensor, and it alerts the admins, management systems, and logs everything. Then representation and keys. Oh god, I think we're in like this last 2 pages. So yeah, hang in there guys, we're almost there. So numbering systems, right? Binary, octal, decimal, and hexadecimal. Again, pretty clear. Binary is just zeros and ones. I mean, you should probably know this as well. The way you can jump between binaries, different binary numbers. You just treat it like a regular number, and when you hit 1, then you just increase the next spacing by 1. It's math, you know. And then octal, it's similar. It's base 8, decimal base 10, the one we're familiar with. Then hexadecimal is base 16. So you have to use characters A to F to substitute 10, 11, 12, 13, 14, 15. So the decimal value of 1011, for example, has to be calculated this way. You take every single digit, multiply itself by 2 raised to its position. So 2 raised to its position from behind. So let's say, I mean, you can pretty much see the example over here. Since it starts with a 1, and this is third from the behind, second from behind, first from behind, 0th from behind, then it'll be 1 times 2 to the power of 3, 0 times 2 to the power of 2, 1 times 0 to the power of 1, and then do that. And then if you add everything up, you'll get the value. Then if you want to reverse it, just keep moduloing it until you get whatever's left. Now we have symmetric and asymmetric key encryption. Symmetric and asymmetric key. Symmetric key just means that there's a private key, right? And then you can use that private key to decrypt it. It's simple, it's normal, it's basic. Asymmetric key encryption is a bit different. You have a public key and a private key. Public keys and private keys are not the same. Public keys are released to the public and reversible, but you cannot get the original data from it compared to a private key. A public key, and especially asymmetric key architecture, is used in digital signatures. So let me explain what a digital signature is now. So in a digital signature, you're doing it for non-repudiation. Keep this in mind, it's a very important keyword. Then, a sender will use a one-way hash function to create a digest, which is like a teeny encrypted part of... No, it's just a teeny part of your work. So a sender uses a one-way hash function to create a digest. It's a teeny part of your message. Then private key is used to encrypt the digest. So now you have an encrypted message. Send it over along with your original work. Now, the message hashed using the function, and the digest is decrypted using the public key. Does that make sense? So you use the function, right, to unhash the message. Sorry, to hash the message. And then you use the digest, decrypted version, which is effectively just the message hashed. Because remember, to get the digest, you need to hash it and encrypt it. Now you're decrypting the digest, which means you're just getting a hashed message, which is the same as hashing the message that you receive. So when you receive your message and the digest, just hash the message, decrypt the digest, you'll get the same thing, and if the two match, the sender is verified. If not, something messed up somewhere. Now for the last part, which is the big part, data structures. This is a bit complicated. First we have, so linked lists, as you know already, they're just tiny capsules that point to each other. You can think of it that way. Variables that point to each other, and the last one points to a null. So it's a head that points to a body, with a head that points to a body, then a head that points to a body, with a head that points to a null. Again, whether it's a head or a tail or a next or a prev, it depends on how you code it, but you just need to know that the way I sketched it out is actually perfect. Then insertion, deletion, they're both off-end. The reason for this is because you have to go all the way to the end, worst case scenario. But for insertion of deletion at the head, it's different, because for the head, you just need to take the new thing, direct it to the first element, and redirect the head to point at the newly inserted thing. So it's easier. Searching again, worst case is going to be M. Then stacks, philo, again, insertion means pushing and deletion means popping. It's very similar to a stack of Lay's or Pringles, because you can just visualize it that way. You put chips inside, if I put red, orange, yellow, green, blue, purple in that order into a Pringles can, right? I can't take out red. I can't like magically will red to like rise to the top. Red is all the way at the bottom because it's the first one that went in. So you can only take out purple. That's how pushing and popping works. Then for a queue, you have FIFO, which is first in, first out. Insertion and deletion, which is on queue and DQ. Again, it's like a queue when you go to queue up and get your food. Simple, don't worry too much about it. Now, we have binary trees. There are two types of binary trees, balanced and unbalanced trees. For balanced trees, you would have insertion, deletion all in log n, and searching be log n. An unbalanced tree tends to a linked list. An unbalanced tree is a tree that doesn't look like this. Let's say 3 is missing over here. Or let's say 3, 1, and 2 are all missing here. Then it'll just become a linked list. Or if 3 and 1 are missing, then it's just a linked list with one tiny deviation. So an unbalanced tree is just a linked list with a bunch of things poking out of it. You can think of it like that. The more it looks like a linked list, the more unbalanced it is. Which is why insertion, deletion, searching are all the exact same as linked list. Whereas in an actually balanced tree, it's going to be log n, not n. Which is also why the way you balance your tree is very important, so that you can optimize all of your operations. Now for the last thing in H2 computing, hash tables. Hash tables use hash functions to index things. There's open addressing or close hashing, and close addressing or open hashing. Please memorize this and don't forget which one's which. So, in A, the hash table size is the number of keys. There's no size overhead or memory overuse. It's all strictly planned and exactly the way it's supposed to be. Then you have, again, very simple. You take apple, you hash it, you get a value, and then you just assign it to that. And if it's missing, you just bring it down by 1. So again, they inserted apple, they inserted banana, they inserted avocado. Maybe avocado equated to 1 and they were like, oh, 1 is already full, so they moved it down to 2. Maybe. That could be the case. Now, for closed addressing, it's a bit different. A closed address is a bunch of linked lists, basically. Look at the diagram I showed you below in B. It is basically an array where each of the elements is a head that links to the rest of smaller linked lists. All of these don't hold data. They hold pointers that point to a linked list. So it is just a bunch of linked lists, basically. So that's why it's so weird. Everything is just a linked list in some way or another. Whatever, programming is beautiful. So then, yeah, no issues of clustering, which means, you know how I told you have to move down by 1 if the space is already taken? There's nothing like that you have to worry about, and it performs way better at the high load. So yeah, that's that. A good hash table is roughly 1.5 times the data size, so that they have the ability to search better, I would say. It's so that there's better spread, and yeah, a more uniform distribution when it comes to that. So yeah, more or less that's all there is for H2 computing. I know it made it sound like it's not that much, but yeah, it's quite a bit. Yeah, just remember, revise, don't panic in the exam. Revise this, and remember, all of the keywords that I stated in here are actual keywords you're supposed to be using. And remember, don't be afraid to chat GPT anything. You can ask me in the comments if you need anything. Ask your computing rep, just bother him. I mean, yeah, it's his job, right? Okay, thanks everyone. I will see you around then. Bye bye.